Hi, I'm Veli from Greenwood Solutions. This week we're looking at the fascinating subject of satellites, space and solar panels. So after watching this presentation you'll understand what kind of solar panels are used in space, what are the actual applications for these solar panels, and what are some interesting future developments. It's a very exciting area. If you like what you see, hit that subscription button. Okay, ready, steady, go! First question to ask is, why is solar technology used in space? Look, solar technology can be a political football on the ground. In space, it encounters little opposition. And this is because the power alternatives in space are politically difficult. The options are radioisotope power systems, or RPS. RPS convert heat generated by the natural decay of the radioactive isotope plutonium-238 into electricity. Batteries have a habit of running low on power, and an expensive spacecraft can turn into space junk very quickly. And few countries want a spacecraft powered with plutonium-238. Governments are not keen on radioactive elements falling to Earth on their population. Effectively, it's solar paired with batteries, and this is the preferred way to power satellites. The space station uses nickel-hydrogen batteries to support its solar panels. Spirit, another Mars rover, also uses batteries paired with solar. Now, the two different types of panels used in space are your traditional silicon panels that are not as efficient as the second option, which is the multi-junction gallium arsenide-based solar panels that have a much higher conversion efficiency, but it depends on the application. Now, for example, the International Space Station uses 16 arrays, and they are using a silicon-based solution, and it takes up about the same size as an American football field, so we're talking a fairly large array, and at this point in time it is the largest space-based solar array. Gallium arsenide is the other solar. These are multi-junction cells made of gallium arsenide and similar materials that resist degradation better than silicon. And they are the most efficient cells currently made, with energy conversions of up to 34%. The junction refers to the number of light-absorbing layers in the cell. Common in space today are 3-junction cells, but 4 and 6 are on the way. So solar panels degrade no matter where they are, and we've covered this in a previous presentation, but in space they degrade even more. So you're talking about the Van Allen belts, those different levels of radiation, galactic cosmic rays, and solar flares and solar winds, all acting upon that cell, bombarding it with radiation and degrading the actual product. So how do they combat this degradation? Well, they can use borosilicate glass panel coverings, and this may be between 5 to 10% efficiency loss per year, because all solar panels degrade. They use other glass coverings such as fused silica and lead glass, and this can reduce the efficiency loss to less than 1% per year. The degradation rate is a function of the differential flux spectrum and the total ionizing dose. In other words, radiation. Solar panels on spacecraft supply power for two main uses: power to run the sensors, active heating, cooling and telemetry, and power for spacecraft propulsion, electric propulsion, sometimes called solar electric propulsion. So the first example of solar and satellites was the Vanguard 1, and it was launched in 1958 under the direction of Dr. Hans Ziegler. It was using solar cells with an efficiency of around 10%, which is quite amazing back in 1958. In regards to photovoltaic research in space, NASA used the Glenn Center, incredibly large area. They have their own equipment in which they can manufacture the cells, and they also test the cells by attaching them to high altitude aircraft, taking them up to a certain point, monitoring what goes on and then bringing them down. Then they extrapolate in the laboratory for space and subject the solar cells to various light intensities and conditions to ascertain that they will correctly perform in space. Now, One of the first questions I asked myself is, how do the panels orientate towards the sun if they're floating around in space? The spacecraft moves and the solar panels are pivoted because that's how they're designed, so they're always orientating towards the sun. It stays in the direct path of the light rays no matter how the spacecraft is pointed. A tracking mechanism is often incorporated into the solar rays to keep the array pointed towards the sun. But sometimes the satellite operators purposefully orientate the solar panels to off-point or out of direct alignment from the sun. This happens if the batteries are completely charged and the amount of electricity needed is lower than the amount of electricity made. Off-pointing is also used on the International Space Station for orbital drag reduction, in other words, to change the orbit of the satellite. Now, China is planning to build the world's first solar power station to be positioned in Earth's orbit. Now, because the sun always shines in space, an orbital solar power station is seen as an inexhaustible source of clean energy. Now, one of the most exciting areas is actually not ground mount systems, not roof mount systems, but space mount systems. Because the sun shines 24 hours a day, 7 days a week in space, the idea was to deploy these multiple small satellites, each with their own solar array. They deploy them, they all come up and they all link up together, right? And they extract the energy from the sun via their solar panels, high efficiency solar panels, and then they change that energy into a radio frequency and basically beam it down to Earth as a microwave. Now, to capture those microwave, they've envisaged these very large nets, approximately 6.5 kilometers across, to capture that energy and then to transform that back into a usable AC electricity. The ultimate goal is to use solar energy to propel spacecraft. NASA has its eye on solar electric propulsion as a way to transport materials to Mars in support of a manned mission on the Red Planet. A key driver of this plan, obviously, is cost. The amount of chemical fuel needed to propel a spacecraft to Mars, along with all the necessities of a human visit, vehicles, power-making supplies, a human habitat module, will be expensive and bulky. Solar power eliminates the need for liquid fuel once all of that equipment is in space. A rocket would still be needed to get it above Earth. Conclusion: solar panels have been used in space for many decades. Both silicon and multi-junction versions are used depending on the application. Future opportunities include a space-mounted solar array and solar-powered spacecraft. Thanks so much for watching our presentation on satellites, space and solar panels. I'm Veli from Greenwood Solutions. If you have any inquiries, any questions, or even any answers, feel free to drop us a line. And if you see fit, hit that subscription button. Bye for now.